We'll talk about today our the final discussion on some different numerical techniques, and as we said last time, they're slightly different because these so-called boundary element methods divide themselves into um, two categories. And basically, the idea is this: we've kind of drawn this figure before of maybe a geometry that we want to define that, for instance, has a tunnel in it. And we know from what we've done so far that if we wanted to evaluate that using what we refer to as domain methods, then that's probably not the best one. We do this. Then we do something like divide it into elements somehow, as we've talked about. And then we'd use those elements to be able to analyze exactly what goes on. So you'll understand that well. But there are another class of problems, or a class of solutions for these problems, which instead of being domain methods, where you have to physically mesh the body, we'll refer to them as integral methods, where you can get away with only representing the boundary. And indeed, so for this particular case, this two-dimensional case really becomes almost a one-dimensional analysis. These elements on the boundary are just 1D, and they would just be these individual segments between the lines that I'm drawing. And typically what they would look like would be basically two-noded elements that would represent the boundary contour, and we'd solve the system only on that contour. And so you see immediately that if you look at, say, if you have you're solving a flow problem, you'd have something like either complementary variables of fluid pressures or fluxes on those nodes, 1 degree of freedom per node. If you look at the degrees of freedom that you have for the case where you have to volume fill with elements, you end up with a much larger system of equations. So you end up with many more equations in this than you do in integral methods. So you have a larger system of equations, but it turns out that the equations you have for domain methods are actually quite sparse. They're quite effective to solve. The equations that you have for integral methods tend to be not at all sparse. They're completely populated, and therefore, even though you have fewer numbers of equations, the operations may still be as onerous, or even more so, than where you have domain methods. The other activity, I guess, is that if you think of this being a tunnel that's in an infinite medium, and you don't care about the boundaries that are around it, then the actual discretization of this would actually just be on the boundary of the inclusion. And so if you're dealing with things like tunnels that are very deep, where you don't care about the free surfaces, or if you're dealing with faults that might be embedded in otherwise porous media, you can get away with really quite small systems which don't need to worry about the external boundary conditions at infinity. And so integral methods have some advantages. They have the advantages that they deal very well with infinite problems. They deal very well with linear problems. And the converse is true for domain methods, is that they deal well with gidgets that are finite, and they also deal very well with nonlinear problems, where you have maybe plastic zones developing spatially within the system, where you physically have to apply a different modulus or a different permeability in regions that are local to where you have that perturbation. And so it's not a homogeneous medium anymore. And so they have different attributes. So we will talk about boundary element methods. You can equally apply boundary element methods to all of the problems that we've solved. So we've solved problems for flow, which are very straightforward. You can use them for transport problems. You can use them for solid mechanics problems. But because these have just 1 degree of freedom and it gets kind of complicated, we'll look at them only for flow problems, actually flow problems, not transport problems at all. So we'll talk about the rationale of how they work today for flow problems. We'll also now, I suppose, make the case that they exist in two different ways, two different forms. And they're sometimes referred to as indirect methods and direct methods. And we will concentrate today on indirect methods. You'll see how they work. Sometimes these are referred to as BEM methods, boundary element methods, and the other ones are referred to as BIEM methods, boundary integral equation methods. The acronym is BIEM. And of course, boundary element methods would cover these as well, but this is often the terminology is given. And so the indirect methods would be sometimes we referred for solid mechanics as displacement discontinuity methods. I'm running out of space methods. Sometimes affectionately referred to as DD methods. Fictitious force methods. Then both of these are for solid mechanics. And you recognize, of course, that when we've solved finite element equations, we've done something like this. So our nodal variables are either forces or displacements. These indirect methods basically are attempting to do one thing. They're attempting to have a distribution of fundamental solutions, Green's functions, that allow you to automatically satisfy the boundary conditions. And since those Green's functions also satisfy continuity and compatibility within the system, then they automatically satisfy all the other governing equations that you have to meet. So the very simple idea of indirect methods is that you place Green's functions around the boundary, work out what the strengths of those would be to exactly mimic the boundary conditions you want, and then you have a solution to your problem. That's the 2-second suggestion of what they are. So in these methods for solid mechanics, you place around the boundary little displacement discontinuities, little cracks that open and have a magnitude of crack opening that will induce stresses at other places within the medium as your fundamental solutions. Fictitious forces are a point force in an infinitely large medium, which give you displacements at some other place, and then you solve again for the boundary conditions. And the one that we'll talk about today is for flow. I don't know it necessarily has a word, but we'll call it fictitious sink. Fictitious, I'm not spelling that very well, am I? Sink, or a source. So innately, boundary element methods, the indirect methods are very, I think, intellectually straightforward. The direct methods are a bit more complicated in that they take the same kinds of solutions, but you have to develop a reciprocal equation that basically allows you to do the same things, to write a larger system of equations, and to solve it in one step. So indirect methods require a couple of things. They require that you solve the system in 2 steps rather than in 1 step. And the 2 steps are, one is to apply a distribution of these fundamental solutions that satisfy the boundary conditions. And then, with those appropriate distribution of fundamental solutions, apply them again to be able to figure out what the complementary boundary condition is at those locations. So in other words, if you have a displacement applied on the boundary, you'd calculate the solution that would give you the right displacement, and then you'd apply that solution again to give you what the force or the stress was at that boundary. And so you solve it in 2 steps. Direct methods you solve once to go through. And so that's what we'll talk about. So we'll talk about the first of those methods, which we said was to look at flow problems. And so the kernel function for a flow problem, the fundamental solution is for a source or a sink. So imagine drilling a small hole in the porous medium and pushing fluid into it so that it goes out from that fluid point. And you can develop elementary solutions for this. So this is a 2D problem. So this is a line source, so it would go infinite distance into the page or into the board, or the screen, I guess. And as a function of this source, you can figure out exactly what the velocities of flow that are reduced at some location a distance r from it are, and also what the head would be at this. So when we've talked about finite element equations, at the boundaries we have either fluxes or pressures. And so the equivalent of this in this terminology are fluxes, which would be the velocities, which have components in x and y, and also the pressures or the heads, which are equivalent. And so the solution for this line source, it's not a point source because it goes infinite length in the z direction. The solution is that the head at any point is equal to how far you are away from that point. It's obviously radially symmetric, multiplied by the source strength. M is the strength of the source, and you could work out what that is in terms of volumes per unit time, but it's the source strength. If you take that head and you substitute it into Darcy's law, which is exactly what this is, then it allows you to calculate, again, the velocities at this point at some distance away from the source as a function of the radius, and also the, this would be the x magnitude, and this would be the y magnitude here. And so the magnitudes of these sources, if you just take this expression here and differentiate it with respect to x, you have to represent r parametrically. I guess r squared would be equal to x squared plus y squared. And if you do that differentiation, you end up with this. So that gives you the equation for a point source. And so that's part of the battle. So the next thing is, let's take that point source and apply it both at a point, but also apply it at every single location along a contour. And this contour is going to be an element that we're going to apply around our boundary. And so we said before that we'd have a boundary that would exist like this, that we'd have individual elements. This element that we'll choose here is going to be a distributed array of sources, which we get just by integrating this expression along the length of this segment. Nothing more, just by superposition. So we can use superposition. I won't do the integration, but the result is that it tells you exactly what the magnitude of the head, and also, let me just, the velocities in the x direction. I guess if this is y, this would be the velocity in the y direction in this coordinate system, and the pressure, no, heads at this particular location. So if you integrate this expression, you get magnitudes for the integrated effect on what the head is at this point, what the velocities in x and y are at this point, and it's just done by integration. So these are the integrals, these are the limits. So this would be the values of the properties at points 1 and 2. Point 1 would be the beginning of the segment, point 2 would be the end, and so this would be just substituting the limits, where this would be x2 log r, whatever this radius x2 log r1 minus x2 plus y2 theta 2 minus the same for all those values equal to 1. So you're just substituting the limits for those for the appropriate locations. And so what that would give you is it gives you a way of being able to calculate a influence function so that the head at a particular location is given by some influence function which includes also this magnitude m. And so we're going to assume that m is a unit strength, a strength of 1. And so one of the parameters that we're going to solve for is what is the distribution of all those strengths m that we have to apply to satisfy our boundary conditions. This is actually one of my favorite classes in terms of explaining this, because I think it comes out to be a really neat discussion of exposition of how it works. So we know what these kernel functions are. These are our Green's functions. Kernel functions with a K. So Green's, I'll use these words interchangeably. And also kernel, K-E-R-N-E-L, as in a kernel of a nut. So a source, yeah, source. And so what these solutions do, if you think about this, is that this is derived from satisfying the equations of continuity, that flows don't accumulate at any particular place, so it's steady state. So it satisfies our differential equation of continuity. Clearly, this satisfies our Darcy's law and continuity, and so that it's satisfying the physical conditions we need to satisfy to get a solution. So it satisfies that. So now if we take this source and integrate it, that still satisfies those requirements. If we take multiple of those integral sources and put them around in a place and use superposition to account for their effect somewhere else, that also satisfies, they still satisfy the governing equations. And so now what we're going to do is we're going to take our system, and let's say our system is well, we'll use a square. We'll do a little example. So we've used this example before. And so we've done, for the flow here, we've had h equals 1, we had h equals 0, you'll remember for sure, right? We have a length of this. I think the example we use is 1 by 1. If the permeability is equal to 1, you could certainly tell me what the flow rate out of here is, right? You can apply Darcy's law, and it's just that velocity is equal to hydraulic conductivity dH dx. This is going to be 1, this is going to be 1, so the velocity is going to be 1. So you can do that. And so what we could do is let's try and solve for this, but let's not think of this as being a block that has a no-flow boundary on the top and bottom and is open at the sides, but let's think about it as something that sits in an infinite porous medium. And in that infinite porous medium, we're just describing the contour of this thing. And so what we could do is we could apply a length of this that has a source, just like this thing here. This is our source or sink. And as a result of that, we could figure out what the influence was, say, on this portion of the boundary, just by doing the same calculations that we talked about before, right? We know this radius, we know these radii, we know the x-coordinates to do that. And so what we're going to do is we're going to work with an infinite medium which is really not punctured. We're going to think about the contour of this, and we're going to apply these sources around the boundary to be able to physically use a distribution of these sources so it automatically satisfies the boundary conditions we have here. And the boundary conditions we have are either going to be defined in terms of fluxes along here or in terms of heads along here. And so if this is our infinite medium, this is our boundary contour that we're just kind of defining two components. This is location, well, we'll call it source, so this is our source. This is our influenced element, if you like, which is this. Then what we can do is we can, in this unperforated medium, we can apply a source or a sink, and we can figure out exactly what the conditions are that it induces here. And the conditions are going to be either in terms of the pressure or head that it develops in this infinite medium, unperforated, or the flow velocities. And so what we'd like to do is we can use these previous solutions we talked about to do that. It's pretty straightforward for the head, right? We can just apply whatever the distances are between these endpoints of this element and the center point of this element, and we could figure out what the magnitude of head is. But we'd like to be able to reduce this down to just only one significant component of flow velocity, not two. We could have x and y ones in terms of global coordinates, or we could have x and y ones, I guess these are in terms of global coordinates, so this one here. But we'd like to be able to use just the amount that goes across this boundary. So what we do is we use the dot product. So the dot product of the velocity and the normal to the boundary vector just gives us the overall magnitude of the fluid that goes across that. We could show it, but I won't. So I can't develop that. And so you can just do it from basic vector algebra of the angles between the normal to the boundary and the actual x and y coordinates we have as direction cosines. These are direction cosines, and I guess this is the direction cosine of 1 minus, or 90 minus alpha. Right? So that's that. And so what we do is we're able to write these equations that we have now, not in terms of the head relative to, not only in terms of the head relative to the source strength in some geometric factor, but also in terms of a velocity, not two velocities, but a combined function that again relates to the magnitude of this strength and the normal to the boundary velocities. And so we'll call that these two functions here. The head at the influenced node as a result of these geometric coefficients and the strengths of the sources or sinks that we apply at the source node here, and then at another one here, and then at another one here, and then at another one here, etc., to make up this boundary. And so we'll have a matrix equation which could define the heads induced as a function of a whole bunch of sources. Likewise, we could calculate what the normal to the boundary velocities would be as a function of those same sources, but the influencing function is just slightly different because it conforms to these components here. And so if we're able to put together a system of equations that does that, then what we could do is we could first make sure that we honor these as boundary conditions, because that's what we want to do. We can calculate what these are, and we can solve for the values of these source strengths. And then once we've solved for these values of source strengths, we can go back and we can now calculate again what the influence functions are, but now the influence functions will be switched to be able to solve for the complementary behavior. And so, in other words, the places that we'd solved for before for prescribed heads to calculate what these are, we now want to solve for the complementary boundary condition, which would be the normal to the boundary velocity at that point. Right? And so, taking it back to this example, we'd put these sources around here to be able to satisfy that we have a head of 1 here, a head of 0 here, and 0 flow across these boundaries. We'd solve for the source strengths, then we'd apply them again, and then we'd calculate what the resulting velocity was here, the resulting velocity was here, and what the heads were at these other complementary positions. So that's basically the idea. And I think it'll all be much clearer when we actually go through an example, which I have prepared especially for you today, and done it many times, but made some actually new visuals for this. So this is the idea. I guess I've said these things, so it's there for reference. We want to be able to define the boundary conditions at every point around the boundary, and we want to solve by placing a source at every single point around the boundary to solve for each one of these boundary conditions. So places where we have heads prescribed, we'll use this equation. Places where we have velocities prescribed, we'll use this equation. And we'll have one of these equations written for every single element around the boundary. So we don't have nodes at the ends of the elements, we just have an equivalent source strength of this strip of element around it, and we look for the values at the center of it. We figure out from those boundary conditions what the values of the source strengths are that satisfy the boundary conditions. Once we have those source strengths, we write the complementary equations. So where we'd written for a boundary condition that's ahead, we now write the equation in terms of a velocity at that location. We know what this is, we can calculate the geometric factor, and we can solve for this. Likewise for the heads. We could also, if we wanted to, not only do it on the boundary, but we could also write those equations for any point on the interior of it, and we could calculate what the complementary conditions were there as well. So it's not just the boundary that we solve for, but we have to satisfy the boundary conditions at the boundary. And so that's it. And so it's relatively straightforward. So this is the part I like. So we're going to do an example. And so the example is one that we've kind of led into. And that is that we have this 1x1 box. It's a porous medium. We have an element along the top with the center of that element at a node in the middle. It doesn't really have a node, but it's at that location. We have an element on the side with another central location, bottom and right side. Boundary conditions are zero flow on the top and bottom, unit flow across heads on the sides. We've already calculated what the flow rates, the velocities would be, right? We know that the velocity is just going to be equal to negative times hydraulic gradient. I think this is equal to 1, but I'm not sure. And so this is definitely equal to 1, right? For this, loses 1 in 1, so the velocity should be equal to 1. So for this geometry, what we're going to do is we're going to write our first system of equations. We're going to write it for the first element. And what we're going to do is we're going to put an element on here and calculate what the induced velocity due to that element is. We're going to put an element here, calculate what the induced velocity at this point is as a result of that element, source or sink. We're going to put it here and calculate the same, and then we're going to put it here and calculate the same. So we'll have one equation. It will give us the velocity induced at this point due to the source applied at this point, which will be the first one of these. So I guess this would be A11 times the strength at node element 1 plus A12 times the strength at node 2 plus A13 times the strength at 3, this one here, and then A14 times M4. And so that is going to be, it's A because it's the one that we want to use that gives us the value of the velocity at that point, because our boundary condition is written in terms of that. And we need those geometric components that do that. Right? When we want to write the constraint equation for this element 2, this equation, the boundary condition is written in terms of the head. And so we'll do exactly the same thing. We'll put a source here and calculate what the influence at this point is. And so this would be a source at location 1, and its influence would be a source at 1 influencing node 2, which is what this node is, and etc. We'd put it over itself and see what its self-influence is. So B22 will be the self-influence, etc. And so we'll go through that. So that sounds a bit too esoteric, but let's do it properly. So let's take these expressions that we have here and let's apply them. And so what I'm going to do, you recognize, of course, that there's an intrinsic geometry that we have in this, in that if we're looking at our cube, we could apply the source at this particular location, or sink. Source and sink are just the negative of each other. And we could calculate what the influence is on itself, the x and y velocities and the head at this point, the x and y velocities and heads at this point, and I guess just from the symmetry, x and y, but really it's only in y, I guess, in this particular case, right? So we can calculate what each of these components are. So by applying this and basically this expression combined to give us the dot products together, we can get the magnitudes of each of these components. And you see this is the only geometry we need because it repeats itself. We can take this as a template and just physically move it around. And so that's exactly what we do. If we do that and we go through this, we see that the effect of having a source element, actually I think it's a sink rather than a source, and its effect on itself. And so in other words, we'll put an element here. So all this is saying is that if we do the calculation for an element that has a particular strength that is equal to M1 here, then the effect itself will be a velocity of 5 in this direction. It'll be actually disappearing into this slit, right? It will give, at point 2, it gives velocity of, this is the x direction, it gives a velocity of 1.28. These are just calculated from that equation. It has a velocity in y. The y direction is down here in this particular case. So this is a velocity of Vy of 1.76. At node 3, the head is equal to 0.0062. And if you look at the velocities, the y velocity is negative. It's 1.47. I guess 1.48. And of course, there's no y velocity because this is on there's a symmetry line that comes down through here. And if you didn't do these calculations for 4, just from symmetry, you'd be able to figure out this should be 1.76, and this should be 1.28. And this particular head is equal to minus 0.27. So this is large negative. This is, I haven't written it here, but what's the head of that particular place? And it's 0.05, which is higher magnitude than this. So so this has to be a sink, right? Everything's flowing towards it in terms of these velocities. Everything is consistent with the lowest possible head at this location, a higher head, and then an even higher head as you get further out. So you could imagine if you looked at this and if you drew it, don't know where I want to draw it. If you looked at this little sink and you drew a contour plot of heads around it, it would just be this elliptical distribution. It'd be like a cone of depression around it on a bullseye. Okay. So this is what I spent a portion of the morning to do. Isn't that beautiful? That's exactly. This is the best. Isn't this the best graphic you've seen all semester? Especially made for you. I can't believe it. This is exactly what we've just drawn, right? So this is with the sink that we have here. Sink because all the fluid is flowing into it of uniform strength. It's just this integrated individual source that's done at every single location along here. These are the velocities that we have as a result of this, and the blue ones are the magnitudes of heads, and it's conformed to exactly what's going on. And so what we're going to do is we're going to use that to overprint on this particular geometry, and we're going to start to try and write our equations based on that. So that's let's get rid of this. Okay? Everyone's still with us? All right. This is what I want now. No, that's not what I want. All right. So this is the demo. Set up slightly differently. Okay, let's see if I can make this work. All right, so I don't want that turned around. All right, so that's the geometry we have. So here, try and move between these. Is it set up? Yeah, okay, it just doesn't like to move. So this is geometry that we're going to want to put together. And so what do we want to do? So we know that at this point, so this is, we're going to write an equation that represents this. We're going to want to represent the boundary condition here, which is a zero flow velocity. So I think it's not, let me just make this full screen. Doesn't really like, yeah, okay. So, what's it going to be? Element 1. What's it going to be? We want to write the normal to the boundary velocities are going to be equal to this sum of what we said Bij times the strengths of the sources. And so what we want to write is that the velocity at 1 is equal to B11 M1 plus B12 M2 plus B13 M3 plus B14 M4. We know that this velocity that we want to represent is equal to 0. It's no flow boundary. And so we have to figure out exactly what these are. So this is by putting a source on the element that we have in question and looking at its self-influence in terms of the velocity it induces. So we're going to put a source on this point here. I'm going to draw this and I'm going to scribble it off. And we're going to see what the velocity is that it induces at this point. So I'm going to kind of remove that because I don't want to kind of mess this up. And so what's this going to be? This is it, right? So we put a source at that node, the velocity normal to the boundary. This is the normal to the boundary. This is the velocity. And so the velocity, the dot product of the velocity is going to be 5, right? Plus 5. And so if we go back to this, oh, it does it for all of them. This is going to be interesting. So this is going to be equal to plus 5 times M1. We're going to put a source in the next element, which is going to be here. And we're going to look at its influence on the velocity at this point. Right? And so if we do that, this is going to be this. So we put a source here, and this is of magnitude M2. It's going to have an influence at this point here. The boundary velocity is in this direction, so the normal to the boundary velocity in this direction is going to be minus 1.28. Doesn't, so I guess L takes it counterclockwise. So what was it? This is minus 1.28 times M2. We're going to put a source here now, and we're going to wonder about what its influence again is on this same location. So actually we're in the right location. And so the velocity induced here is going to be 1.48. Again, we're interested in the normal to the boundary velocity, so it's minus 1.48. Oh, yeah. So it's minus 1.48 times M3. And we're going to do the same with the final location, is we're going to put something, we're going to put something on here. And we want to know what its influence on the velocity is here. Won't leave that on there. And of course that is, I guess, this. So the velocity is here. It's normal to the boundary that we want. So it's going to be minus 1.28. Times M4. And we know that equals 0. Okay. Next equation. What we're going to do? We're going to want to solve for the behavior here. This is prescribed as a head. Head is equal to 1 on this boundary. And so we're going to write our alternate expression, which would be equal to H2 rather, isn't it? Is equal to A12 M1 plus A22 M2 plus A. So it's the other way around, isn't it? This is 2-1, this is 2-2, this is 2-3 M3 plus A 2-4 M4. Head at 2 is equal to 1 on the boundary. And we have to figure out what these influencing functions are. So the first one will be, we'll put a source at node number 1, element 1, and see what the influence is on number 2. And so we're going to put something here, and we're going to see what its influence is on here. This is much easier now because we're calculating what the head is at this point. And the head is a scalar, so we don't have to worry about the normal to the boundary vector and all those things. And so if we go back to this, This is a unit source of magnitude m1. Its influence at this point is going to be this value of head, so it's minus 0.05. Oops. Let me just get rid of that. Why do I do this? And so you get the idea that this is going to be equal to minus 0.05 times n1. So who's going to tell me what the next one is? So we're going to put something on here and look at its self-influence. And so what's the value that we're going to want to use for that? Who's feeling brave? No, self-influence, right? It's going to be, the source is here, and it's going to be its influence at this point. So it's going to be 2.7, right? So the second one, so what we're going to do is we're going to, we're going to put one. So we're going to put a source on this, and we want to figure out what its self-influence is at this point, because that gives us this second one. So it's a source at element number 2. The influence of that source on number 2 is its self-influence. So it's going to be, if I get rid of these, .27, right? 0.27. Say it again. Which, say it louder, sir.
I think this surface is the 1, and the surface 2 was the 1, isn't it?
2, no. This is 1, top. This is 2. They're number clock. Isn't that right? Good question, actually. I guess that's on this other plot. This is the right orientation. Yeah. 1, 2, 3, and 4. No, stop. Yeah, stop. Fine. Yeah. No, I think we're okay. And so this is 0.27. Did I put it on already? I'm not sure. This is M1. Whoops. What was it again? No. 0.27? 2.7. Oh yeah, okay, it was. Yeah, it disguises it. And so the next one would be 1 on the third element, 1 put down on here, and its influence on this one. And so that would be this, as it turns out. So it would be 0.05. Minus 0.05 times M3. And just for completeness, let's finish it off. We're going to put 1 on here, and we're going to see what its influence is again on this one here. And so this is going to be this one, 0.0062. I think it's positive, right? 0.0062 M4. And so you get the picture. The next one on the bottom, if you remember, so this is, on the top it was no flow boundary condition. On the side it was a head. This is again no flow, so it's going to be something like V dot N3 is equal to the sum of B, I, J, MJ. I won't go through them. And then the final one will be a head, which will be the head at 4 is equal to the sum of Aij, MJ. And so those together, if you write them out in terms of just this value, the left-hand sides are going to be the velocity at 1, the head at 2, the velocity at 3, and the head at 4. All the terms that we have on this left-hand side here. This is 0, this is 0, this is 1, and this is 0. And so these coefficients multiplied through by the weights is just going to be a matrix relationship. And it's going to look exactly, it's easier to write it as a matrix for me. We've done this many times in this class, right? It's going to be the strength of the sink when it's overlaying element 1, strength of the sink on 2, 3, and 4. And we don't know any of these. These are what we don't know. And the values of these that we go in here, this is plus 5. This is minus 1.28. This is minus 1.48. And minus 1.28. And you can do the same for these as well. Minus 0.05. So I won't go through the rest of those, but that's what it is. So we know all of these influencing functions. These are our A, B's, I's, and J's, right? So they're mixed depending on the boundary condition. But we know the left-hand side. We don't know the right-hand side, but we know all the coefficients. And so now we can solve for it. And so what I didn't redo very nicely was this. So you have this in here. So I added these. So the very final version you have of this in your notes is the appropriate ones. So this is, you'll see this. So this is, in one page, this is exactly what we're doing. What we've done is we've written a matrix which has the influencing functions in it. It was 5 on the leading diagonal, minus 1.28, minus 1.47, minus 1.28. It was minus 0.53, etc. So these are the influencing coefficients. If you solve for these values, you get magnitudes of these fictitious sink strengths, which are M1, M2, M3, and M4. So those don't mean anything. Those just happen to be source strengths that we can now calculate. But what they are they're distributions of source strengths which give us the boundary conditions, because we've enforced the boundary conditions in solving this equation. Right? We've enforced the boundary conditions. We've known what these influence functions are, and therefore we've been able to figure out exactly what these are. So we now know what these are. So now we do the converse. We go back and we can write the equations exactly the same as we did here, but now at this top surface, instead of wanting to solve for the value of the velocity, which we know as a boundary condition, we'd like to know what the head is. And so instead of writing the equations in terms of this at element 1, we'll write it in terms of the influence that gives us the head at that point. And so the next step, I guess, is, if I zoom, I think, yeah, so that's all I'm going to do. So now, so this is solve for sink strengths. And so the next one is to solve for complementary boundary condition. Right. So just to help us out, I'll draw our little map up here in terms of what these were. This was velocity, this was head, this was velocity, and this was head. This is 1, 2, 3, and 4. And so now we know what the magnitudes of, say, M1 is, and M2 is, and M4 and M3. I guess I wasn't going to write those in, but we know what those strengths are. So now we want to solve for the complementary values. Head at node 1, velocity at node 2, head at node 3, and velocity at node 4. And so if we start again for element 1, what do we have? We want to solve for the head. So H1 is equal to A11 M1 plus A12 M2 plus A13 M3, etc. We know what these values are. We don't know what this is, and so we want to be able to fill this out. And so we can go back to this again. So what we're going to do, we're going to put a source on element 1 and see what its self-influence is. So this is element 1. We're going to put a source on it. Self-influence on a source at element 1. A11 is going to be 0.27. It's actually much easier to do this on an overhead projector, actually, where you just have 2 sheets on. So what do I say? 0.27. And the head we don't know, H1. We do know what M1 is. The source at 2 and its influence on 1. So we're going to put a source here. We want to know what its influence is on the heads at this point here. And so source here, influence here, 0 plus 0.05. Don't really. Source at 3 and its influence on 1. That's going to be a source at 3 right down here. Its influence on 1 is going to be 0.0062. Times M3. And finally, we're going to put a source on this side here and find out what its influence is there. And that's going to be 0.05. Right? This influencing this point here. .05 times M4. And so we can also obviously make a makeshift equation, but now this is actually useful to us because we can do the forward analysis. We know what the values of M1, M2, and M3 and M4 are. We know what these influence coefficients are, so we can directly calculate what H is. And we can do that, we can repeat that then for the velocities of the other place. And so we end up with this inverse relationship, which, if you want, how did we do it before? If you want to write it out in longhand, what's it going to be? It's going to be head at node 1, velocity at node 2, head at node 3, velocity at node 4. We know all of these coefficients, the first ones we have there, right? For equation 1, 2, 3, 4. And the source strengths we know. So we know all of these, and we know these are things like plus 0.27, 0.05, etc. And so we're able to calculate what the complementary conditions are. That's it. So step back. It's been a lot of kind of juggling things around, but basically the idea is you have a fundamental solution that satisfies your governing differential equations, satisfies continuity for flow, and it satisfies Darcy's law substituted into continuity. It satisfies that on its own, and by superposition, if you have a whole bunch of them, it still satisfies that behavior. You can show that it's so by substituting it into the governing PDEs. And now you want to drape those around an infinite porous medium where you have the contour defined, and you're putting these solutions around that unperforated contour, if you like. And you're adjusting their strength so that on all the other boundaries, it's just right that it recreates the boundary conditions you have. That gives you the distribution of those source strengths that you need. And of course, that doesn't seem like any solution. But the solution is that you want the complementary boundary conditions, or complementary conditions on the boundary. And so when you had velocities prescribed, you want to calculate what the heads are. And so that's why you have this two-step process. Figure out what the source strengths are first, then apply those source strengths, which is what we've just done here, with the complementary equations, where we'd use the A's before, we now use the B's, etc. And then we solve for this magnitude here. And again, it's all done on this horrible thing here. I say horrible. So the first equation we wrote today was this forward expression here, which we satisfy boundary conditions and we solve for source strengths. This is quite old. This is a dot matrix print. I'm not sure whether you know it. Do you know what dot matrix printers are? Perhaps not. Yeah, so anyway, technology from the past. Then you do the opposite. You know what the source strengths are, and you create these other conditions. So this is our, should be 0.27, 0.053, 0.006. I'm guessing that's this. 0.27, 0.005, 0.006, etc. It's just the top line of this. And when you use this equation with these known source strengths, the value of this vector here that you get out of it is the very last vector on that page. And I think this is just a Fortran code that I wrote to solve an equation, maybe 25 years ago. But, so this is what? This is the head at node 1. This is the velocity normal to the boundary at node 2. This is the head at node 3. And this is the velocity normal to the boundary at 4. And so, do those make sense? This is our geometry. The distribution of head across our system would go from 1 at the upstream to 0 downstream. So at the middle of this nodes, at nodes 1 and 4, you'd think that the value should be about a half. It's not. It's 0.43 and it's 0.43. So it's a little less. Almost. And the velocity across here should be from high head to low head. We've used Darcy's law already. Hydraulic conductivity, dH dx. I think the hydraulic conductivity I used is clearly not 1. I think it's 10, just from looking at these. And of course, if that's the case, then this velocity should be 10, and this velocity should be 10. This is the normal to the boundary, outward normal. This is the normal to the boundary, outward normal. So this would be minus 10, because it's in the opposite direction to the normal. And so that's this value here, minus 14. And the value out here is in the same direction, and this is plus 9.3. That's not great. And so that's it. So the results aren't quite right. Why do you think the results aren't quite right?
Just for
Yeah, discretization. Bad discretization. So that's it. And so that's it. And so I kind of enjoy that because it really is very simple. I mean, I won't repeat it, but the technique is very simple. You just apply sources of some description to be able to satisfy the boundary conditions. If you're solving a solid mechanics problem, then the sources that the Green's functions you're applying are for a crack opening, where you can calculate the stresses and displacements away from that crack, and you have those cracks distributed around the boundary to be able to satisfy the boundary condition. And you do it in the same 2 steps. You satisfy the distribution of cracks opening in normal mode and in shear. You end up for n boundary elements with 2 n equations, one for shear and normal displacements, and for boundary conditions in terms of maybe shear stresses and normal stresses. You solve for the distribution of those little cracks, the strengths of those cracks, how open they are and how sheared they are. and then you do the reverse substitution to be able to impose those known strengths, but use the functions that instead of giving you the stress boundary, the stress condition at some location, maybe the displacement condition. And so they fit into that mode. So that's it. So I think it's, sorry. I hope you enjoyed that. I did. Sorry. You could tell I did. So that's one method. So he said that all of these boundary element methods require that you only discretize the boundary. What we didn't say here, I guess, is that you could also write this equation now for a point. You could write it for an equation here. So in other words, you could apply the, now that you know what the conditions are, you could write a source at the boundary for a known magnitude and calculate what the heads are induced in the middle due to a source put here and then a source put here to calculate these effects, and then one boundary. So in other words, if you know what these four source magnitudes are, you can write the equations in terms of the A matrix, to figure out what the influence functions are for these four sources of which magnitude you know here, to now calculate what the head is at an interior point. So even though you're solving only on the boundary, you can also calculate what the conditions are inside your system as well, in terms of heads and velocities. You can calculate them everywhere. And so that's one thing that we should make the point of. A more convoluted way of doing this is the so-called direct methods. And I won't go through this in any great detail, but it uses basically the same idea. And so now what it does is it takes a unit function, our source or sink term, and it applies it at a point on the boundary. And this unit source it uses to at every other location around. So you put the source here, and at every other location around the boundary, you calculate the induced head and the induced velocities in an unperforated medium in the x and y directions to get the normal to the boundary ones. And the only difference is that you write it in the form of a boundary constraint equation. And this boundary constraint equation, for one particular influenced node, looks something like this. It has a free term on the front, multiplied by the magnitude of the head at that influenced location. And it has an integral, which is the product of two things. The magnitudes of the heads that are imposed at that particular location on the boundary, but also an integral which represents the effects, if you like, of applying a unit source here, of unit magnitude, unit m if you like, and what the values of the velocities, normal to the boundary velocities are at every single influenced location in sequence. And so you end up with a whole series of these magnitudes which have to be integrated over the length of the element that they're influencing, which is really no different from what we just kind of did already by integrating the expressions. But you also calculate, as a function of applying this source, what the magnitude, influence of magnitude is in terms of the heads that are induced at that location. So you're doing the same thing. You're providing a source at each location in sequence. You're calculating what the velocities and heads are at the other locations. And instead of doing it in two steps, you apply the source to get both the induced velocities and the induced heads at these other locations. And then you write a big matrix equation, which is will basically look like a matrix of velocities multiplied by a vector of heads. And you set that equal to a matrix of these head magnitudes multiplied by normal to the boundary velocities. And so if you have a total of n nodes, this will be n by n in size, and this will be rows and columns, rows n by 1. This is n by 1. So this is just a vector of the heads that would be present at all the nodes around the boundary. And this would also be n by n and n by 1. And so these kernel functions, these integrated kernel functions that we have here, we can get in the same way that we've kind of done it, the A's and B's that we had before. And so what would it be? These would be the B's. These would be like the BIJs, and these would be the AIJs in this expression here. So we can get these. But if you think about these nodes around the boundary, and it typically is done in terms of nodes, just like finite elements, then what happens is that here we might know the heads, and the heads, say 1, 2, heads 3. But for other portions, we might know normal to the boundary velocities. So you could imagine that nodes 1 through m and m plus 1 to n. So I'm just making it overly complicated. So in some of the nodes, we'd have values of heads. So if you thought about it, you could divide this up into two kind of submatrices, where we have heads on segment 1 and the velocities on segment 2. And we'd know absolutely the velocities on segments 1 and the heads on segment 2. And so say we know these conditions. So this is, let's call this segment 1. Let's call this segment 2 where we know the velocities. And so in terms of the boundary conditions, we'd know all of these heads, and we'd know, did I write that? Yes, I did that incorrectly, didn't I? So this, of course, should be heads 2, H2. And this, of course, should be V dot N2. This is just this equation. So if you divide each of these vectors in half of the first values would be the heads at nodes where the heads are nodes, and the second ones would be heads where we don't know the heads because we know the velocities. And so the only point I was going to make is that we know the heads at these locations, and we know the velocities at these locations, and so we have a total of n equations to solve. We have a total of n boundary conditions. Some of them happen to be heads, some of them happen to be velocities, but we can just rearrange these equations to solve the system equations by basically swapping rows and columns until we swap these things over here. And that's it. So I mean that's probably really all we have to be able. So this perhaps says it a bit better. So this is in your notes. So in other words, we have these cases. So in the cases where we know the heads, then we know maybe I guess it depends how you number them. Let's see. No, I guess it's this. So I guess this is contour 2, and this is contour 1. I think that's right. Let's see. Let's see. Rearranges. No, the other way around. This is 1, where we know the heads, and this is 2. So this would be 1 and 2, same as before. 1, 2, 1, 2. And so we know the heads at location 1. So we know these, and we know these. And so what we're going to do is we're going to rearrange these equations in terms of those values. Yeah, okay. Yeah, so we know this at node 1. So in other words, we want to do the matrix swap for these rows and columns, so we end up getting V2 into this location here, just by swapping the appropriate rows and columns. So now we know each of these. We know absolutely all of the terms in this, in both of these, but we don't know the values of the velocities on segment 1. So the velocities here are unknown, and the heads here are unknown. So heads on 2 and velocities in 1 are both unknown. And so we can multiply both by the inverses. I guess I've done it the wrong way around. Right? No, it's right. Okay, so I guess all of a sudden V1 is just written a bit confusingly here. We've multiplied both sides through by this matrix here, and I've switched these. And so H1 and V2 we know. Velocities on 2, heads on 1 we know. We know absolutely all of the terms in both of these matrices, and we can solve for our unknown values that we have here. And so we basically end up doing that. And so in the same way that we have isoparametric elements for finite element problems, you can also have isoparametric elements for these. Won't go through that. But just to notice that, so what's different with this, obviously, is we've solved in one step. We've written this much more complicated system of equations, which is this. But when we solved it once. We didn't solve for the source strengths and then solve by resubstituting source strengths and solve for the other complementary conditions. We solved it in this one step. So we can make these things into isoparametric elements. I won't talk about that. But the other thing you could imagine here is that if you think about this matrix equation as we have it defined here, and if we write it as this. So maybe if you think of this expression here, we could also write this expression as lowercase v on this right side is equal to the inverse of the upper H matrix, the V matrix, the big matrix, and the heads. So I'm just rewriting this in terms of the heads, which are here, the big V matrix, which is this one, the big H matrix, which I've inverted in this. And the point is, if you look at this and you multiply velocities by areas, you have Q equals KH. And so if you think about this, you can use this technique as well to be able to basically write a conductance matrix using just these boundary elements to be able to interface finite elements and boundary elements together. And this guy's going to come and open the door on me a second. And so if you want to, you can actually interface these by using the same kind of, and this is the discussion how to couple them together, is just by trying to make super elements. So this could be our geometry that we just solved for in our very simple example, but instead of using 4 elements, we're using 1, 2, 3, 4, 16 elements with nodes at each end, and then attempting to interface this big conductance matrix with a whole bunch of smaller finite element matrices. And so there's a little bit of discussion on that, and here's a paper I just threw in to kind of show you the idea, is if you wanted to, you could embed a finite element mesh inside a boundary element mesh to be able to interface the solution techniques together where they both satisfy their intrinsic capabilities. Integral methods, infinite domains, they can go forever. They work really well in those systems, but they like to be linear. And so maybe you could have a zone which is close to a wellbore where you have high velocity flows and maybe turbulent flow which is nonlinear, and you represent that interior zone by finite elements, and the exterior you represent by these infinite elements that go away. And so this was just an exercise to be able to just see whether that can be done. It wasn't the first time it had ever been done, that's for sure. And just to see whether it works out. And so in doing things the way that we just talked about it, in terms of being able to write this matrix equation, I'm trying to see if it's in here. No, it's not really obviously written. But by trying to interface them in this way, you can write the boundary element methods using the direct method, the one-step solution method, to write it as a conductance matrix, or for solid mechanics problems as a stiffness matrix. And you just treat it as a big finite element, which has the same degrees of freedom numbering patterns that we use in our other calculations. So,